Today we're going to be learning the Dijkstra's algorithm. Dijkstra's algorithm. And in this algorithm uses BFS on a graph structure. So on a graph structure to find the shortest path from S to any node in this graph. It does this by also employing a priority queue to figure out which path to traverse next. So say the starting node S had three choices. It had 5, 3, and 2. 5, 3, and 2. The priority queue, perhaps this is a heap structure, a min heap structure. It's going to queue the edges to explore in this fashion. The way Dijkstra's algorithm works is that it assumes every time it finds a path to each node, so this node here, A, it's going to assume that every time it moves away, that the weights, that the paths are only going to increase over time. This is also the downfall of the Dijkstra's algorithm, as if there's a node C that sort of goes back to itself or goes to another neighbor with a negative edge weight, Dijkstra's algorithm is not going to assume this. It may lock in C to be the only possible weights, and while a negative weight lingers on, the Dijkstra's algorithm is not going to catch this. So this only works on positive edge weights. Let's see how we can run this on a graph. So let's solve this graph together. Let me get a good line here. Let's keep track of our I steps. Let's keep track of the I steps that we're using. And let's keep track of some sort of big S here, which are all the sets that we're going to sort of use over time. So let's solve this problem. We have an I here. We have our sort of big S. This is our set that we're going to be working with. And then we have all of these nodes that we're going to be tracking. Now we start out with an empty set, and this is sort of like the zeroth run. And we're going to have 0 here, and we're going to assume everything here is infinity. So these are the closest distances to S. These are all the closest distances to S. And S is always 0 because the distance from S to S is 0. So we start out and we lock in 0, and we throw this into our priority queue. So our priority queue has S in it now, and now from S, we're going to look at this table above. So we're going to see 2, 5, and 1. So A has 2, B has 1, and C has 5. Take the smallest one, and let's lock that in. So we're going to do a set of S. We have a set S and B. We have S and B. And now what we're going to do is now we're going to look from B. And we're going to see from B, we found C with 4. We found C at 4. So we're going to make C now 4. And then there's nothing we can really do after this iteration. So we bring back this 2 down here from A, and then we can now lock in A. Now our next set here is going to be S, B, A, and then A. What A sees, it sees that D is 9 because 2 plus 7. So it's going to see that D is 9 because 2 plus 7. So D is now 9. So we're down here. D is now 9, and what else does it see? It sees 2. So this is 2 plus 2, so 2 plus 2 is E. And E is now 4. We have 4, and that's all we could see. So we bring down everything, again, that isn't locked in. Now we look at our set. We can either choose C or E. Let's just choose C, because we saw it first. And now we're going to do S, B, A, and what did we just lock in? C. Locked in C. And now we're going to see that, okay, from C, what do we see from C? We see F. So 6 plus 4, 6 plus 4, that would be 10. So f is 10. So this route accumulates to 4, so that's 10. Now we see e, so 4 plus 1, that's 5. It's not bigger than this one down here, so we're going to keep e where we found it, and then seems like that's all we can really do for this round. So let's copy down what we didn't lock in. So 9 for 9. Now we can lock in this next 4. Now we can lock in this next 4. Now e, now we're looking from e. If we look from e, we can see that 3 plus 4 is 7. 3 plus 4 is 7, so that's smaller than what D has now. So we can put 7 down here. That's smaller than what D has now. And we see another path to G. We see a path to G. So 8 plus 4, 8 plus 4, we are going to get 12. We are going to get 12. So now that's all E could see. That's all E could see. So let's just bring down everything that we haven't locked in. And it looks like I haven't been updating the sets over here. So we're now at S, B, A, C, and then we locked in E. This next thing we're going to lock in. So S, B, A, C, E. Next thing we're about to lock in right now going to be this 7. That's D. So the next thing we're going to do is use D. And so 7 plus 1, that's 8. So 8 going towards G. That's better than what we have now. So 8. And then that's all D can see. So we copy down again what we didn't lock in. We lock in 8. We lock in 8. So now S, B, A, C, E, D, and G, and G, and then we can look from G. Well, there's nothing we can do with G. There's nothing we can look out for. And 10 is the last thing we can do. That's the last thing we can lock in. We lock in from 10, and everything else in this sort of table is less than 10. So that's just sort of the end. So the last one would be S, B, A, C, E, D, G, F. And let me write it more clearly up here. That would be S, B, A, C, E, D, G, F. And I forgot to put this 2, 3, 4, 5, 6, 7, 8. That's how you trace Dijkstra's algorithm. So here's the code for Dijkstra's algorithm and implementation of it. Before we jump into this, the way that we're sort of utilizing tuples here, so a tuple is a pair of numbers, so some pair of numbers. The way that we're using this tuple here is that we set the edge weight at the beginning, the edge weight at the beginning, and then the actual sort of variable, the node, as the second member. So the 0 index is the weight, and the 1 index is the node itself. This is going to help us, this is going to allow us to sort of store in a min heap and keep track of what nodes track to what weights track to which nodes. So things I like to point out, here we're setting everything to infinity, like what we saw in our traversal that we just did, and we're going to have just we're going to run regular BFS. Here we're running that tuple min heap, so we're creating that min heap of tuples that we need, and we first insert the starting node that we need, so S0. Here we're just running regular BFS, so we start, we pop it off the queue, and then we're going to evaluate the next edges to add to the queue. So here we're going to evaluate what the next possible edge could be. So here we got our new C edge, possibly coming from S, possibly coming from something else, and we're going to see next is going to be the edge weight here and the node. And now if this hasn't been visited, we're checking if this node hasn't been visited, we'd like to insert it into the queue. And we'd also like to check if this weight we just found is better than the distances we have right now for this node next. And if it is less than, we want to set that to the new distance that we just found and change the parent of this node to the node that we just came from. So the node we just came from was this. We popped this off the queue, so we pop this off the queue. And we're now saying this next node that we just found, taking this off of BFS, this is going to be the new parent. That's why we had this parents table. And then return the distances and the parents. Now, what is the runtime of the Dijkstra algorithm? The runtime is going to be O of n plus m, as for n nodes plus m edges. As when we have a hash table, we have sort of n entries, and there are m connections, so every connection counts all the way up to m. So we, over the course of this entire algorithm, we did n plus m, which is basically the runtime of BFS. And that is the end of this video. If you enjoyed it, don't forget to like and subscribe. If you are looking for this code implementation, you can look in the description below. You can open the implementations folder and you can find this code there. This is an open source repository, so pull requests and issue requests are fully appreciated. And with that, thank you.